In order to avoid the potential issue of combusted borane solid particles interfering with the operation of the turbopump, whereby the boron particles would cause erosion in the turbine of the turbopump, a potential solution to this issue would be having a separate kerosene combustion system to provide propulsion to the turbopump and using pentaborane as the main rocket fuel, where most of the weight savings are going to be realized. And between 1 and 3% of the fuel, depending on how much you would have to burn to power that turbopump, assuming 1 pound of fuel and maybe 3 pounds of oxidizer to power the turbopump combustion, the gas generator of the turbopump, the burner for the gas generator of the turbopump, would potentially consume about 3% of the total rocket fuel. Then one could realize very significant savings by using pentaborane in payload, again in the order of around 60%, in this case reducing that by 3%. But one could possibly design a turbopump which has a dual system where one turbine blade is temporarily shut off, cleansed of the particle accumulation, and then switched back on. And that process would be repeated in order to avoid excessive buildup of boron particles. Depending on the velocity of the gas, the combustion gases, erosion could potentially be mitigated by reducing the velocity and increasing the pressure. So by going through a diffuser, a divergent nozzle, one may be able to reduce the velocity of the gas and attain very high pressures in order to power the turbopump that way. I think that would be a viable option if an auxiliary kerosene-powered turbopump or UDMH-powered turbopump. I mean, the energy density of UDMH is about half that of kerosene, but there are potential solutions to powering a rocket engine with pentaborane B5H9, unlike it being unlike with jet engines where there really is no viable option on the table that allows one to use pentaborane, considering the serious erosion damage that would be entailed, especially in the high pressure section of the turbine. There might be materials that are more erosion resistant, such as ceramics. This fuel was tested in the 1960s when turbine blades were nickel alloys. I don't think they even had developed single crystal alloys during that time. Today, with ceramic matrix composites, the density of boron, if the density of boron is lower than the CMC composite material, then we might see minimal erosion. If the density of the boron is higher, then we might see erosion as a significant issue. I will have to check the density. I believe the density of boron is relatively low, hence its low atomic weight. So I think there are definitely solutions to powering a rocket engine with borane, and there might even be in the future solutions to powering turbo jets, especially again afterburners. But again, I think the most attractive propulsion system to be used with borane fuel is either ramjets or scramjets. Scramjet being the combustion is supersonic, and a ramjet being that the combustion is the peak flame speed is below. Or the speed in the combustor is below supersonic. From what I understand, or that the air is slowed down to with a diffuser below the speed of sound. But anyway, the point is, I think that in a borane rocket engine, either an auxiliary turbopump propulsion system is provided, or the impellers of the turbopump are designed with ceramics and or a special kind of system which mitigates the erosion and or buildup of solid particles in the turbopump impeller. So that's all I have to say for today.